Hello, this is a video for AP Physics 1 centripetal motion with banked curves at an angle with a horizontal. Case number 1 is going to be with no friction. So we have a banked curve. Banked curve is by definition a little incline at the turnings so that the car could keep its circular path when it's making the turn. So the incline at an angle helps that do it. So if you would see the free body diagram, keep in mind that centripetal force will act towards the center to keep the car in circular path. And keep in mind, when we are splitting the components, if you would see, we are splitting the force normal to cosine and sine theta versus mg that we do normally on an inclined plane. The main difference is on an inclined plane, the object slides up or down and influenced by the gravity. And here it is going horizontally on a circular path. So keep in mind to split your force normal into components. So normally we will sum your Fy forces, which is mass times acceleration in y direction. Here it's 0. So, but the y forces that we have are n cosine theta and mg. So it's going to be n cosine theta minus mg equals 0. And I'm rewriting in the force normal n equals mg over cosine theta. You can pause the video and set it up and write it and follow it as long. And summing the f of x force in the x direction, which is equal to max, since the acceleration in the x direction is going to be the centripetal, we equate it to mv square over r. In the x force we have in this is just n sine theta, which is acting in the same direction as your fc. So we have n sine theta equals mv square over r. So you can rewrite n equals mv square over r sine theta. Since the force normals are same, I'm equating it and I'm getting v equals square root of rg tan theta. So this is a critical velocity for the cars to keep when there is no friction. If the car has a velocity greater than the v, then it's going to move up the curve faster and then or slide down when it's less than v. The second case that we will be talking about would be with friction. That can give us other possible options to have different velocity and keep that in curve. All right, the second case where you have with friction. So like I said, the friction is going to help in a scenario where when it's less than v. If you would think about it, if you are saying that if it's less than v, it's going to slide down, which means the friction is going to act up. So we split the friction into components, frictional cosine theta for x and frictional sine theta for the y. And if we rewrite our sum of the y forces, we will have n cosine theta acting up, frictional force sine theta also acting up, mg acting down equal to 0 since we don't have acceleration in the y direction. Whereas for the fx, force in x direction, we have n sine theta and we also have frictional force cosine theta in the opposite direction, and they both equal to mv square over r. So what I've done is we also know that frictional force equal to mu n. When you plug it in and you want to kind of isolate your force normal in both cases, fx and fy. So you will have n equals mg over cosine theta plus mu sine theta, and n equals this. Since both are force normal, I equate both sides and isolate to find the velocity. If you would see in this case, mu plays a role to get your velocity that's not just critical, right? Like, so it is able to have a velocity less than v, like we did it. If you would rearrange this and you plug in mu equals 0, you are going to go back and get the same velocity as in case 1, square root of rg tan theta, where when your mu is 0. In this case, since we have friction, mu plays a role and gives an more leverage on the velocity that the cars could have when it's turning the banked curve. Hope this helps. Thank you.